This is the electronic balance board or wobble board. I'm going to show how it works and then I'll explain how to make it. The electronics for the balance board are turned on with this switch. And then when you press this button, the timer will start. And the time will run as long as the outer rim of the board does not touch the ground. But then if the board gets out of balance and touches the ground, the timer will stop. The end time will remain on the clock until the button is pressed again, which starts a new timing session. And again, no matter which way the board touches the ground, the timer will stop. So I will show how it works with somebody on the board. You press this button and the timer starts. And then you balance on the board until it touches the ground. And then the timer ends and it keeps the time that you were balanced on the board. I will point out the various parts of the board and how to assemble them. Here is a list of the parts, along with how much each part costs, and I will leave a text description of each of these in the description box below the video. The main item is this Amazon Basics Wood Wobble Exercise Balance Board, which can be purchased from Amazon for $17. The next part is the DAIERTEK 9-volt battery holder with on-off switch and the lead wires. Inside the battery holder is a Duracell Coppertop 9-volt battery. For displaying the time, we use a TM1637 4-digit LED display module compatible with Arduino. The button is a DAOKI big button module, 12 by 12 millimeter, high level output. Also, each of these components is attached to the board using Velcro, in this case the Melsan 1 by 4 inch hook and loop strips. And the adhesive holds the bottom piece to the board, and the other piece is also adhesively attached to the component. And then using a drill, a hole is drilled off-center on the board, big enough for 9 wires to fit through. And that hole goes from the top of the board to the bottom of the board. I use an open box as a stand to hold the board so that the electronics on the top don't get damaged while I work on the bottom. The bottom of the board has this plastic piece that is screwed to the board, and the electronics are housed within that plastic piece. I have removed the screws using a Phillips head screwdriver, and now you can see the plastic part comes off. The electronics are inside. On this plastic member, the internal supports previously came all the way to the top and met in the center. An oscillating saw was used to cut an opening to fit the electronics. The 9 wires from the devices on the top of the board come through the drilled hole. The sensor here is an MPU 6050 6-axis accelerometer that's used as a tilt sensor. It has the pre-soldered leads for the wire connections, and it's also been placed on a pad and gorilla glued to the exact center of the bottom of the board. For holding the chip and also making the wire connections, we use a REXQualis 400-point small solderless breadboard. The chip being used is an Atmega 328P Arduino Nano version 3.0. As a side note, the two battery leads have been extended by connecting them to female to male wire connections. Here's a list of all of the component to Arduino connections. The battery leads are connected to the Arduino VIN and ground pins. The accelerometer VCC is connected to the 5-volt pin. Ground is connected to ground. SDA pin is connected to the Arduino A4, and the SCL is connected to the Arduino A5. The button connections S to D2 on the Arduino, V to the 5-volt pin, and G to ground. And for the LCD display, the clock is connected to D4, the DIO is connected to the digital pin D5, VCC connected to the 5-volt pin, and ground connected to ground. All of these pins and leads are labeled on the components. I also note that I use male-to-male connectors to connect the 5-volt and the ground pins of the Arduino chip to these outside rails so that all of the 5-volt and ground connections can be made on those outside rails. Here are some preliminary instructions on how to program the Arduino. You first have to download the Arduino Integrated Development Environment. You can download it from the website shown there in item 1. You connect that to your computer with the provided USB cable. Select the Arduino board in the Tools menu, and then select the connection port also in the Tools menu. For the LED display, you have to install the TM1637 library, which can be obtained through the Sketch Include Library, Manage Libraries, and locating the TM1637 library by Avishai Orpaz and clicking Install. Similarly, for the sensor, you have to install the MPU 6050 library. This can be obtained also through the Sketch Include Library, Manage Libraries, and the MPU 6050 library. Click Install. Here is the code for the balance board, and I'll just provide some notes as to various items of the code. You have to include the header files for both the LED display and the sensor. Provide instructions as to which pins of the Arduino the various components are connected to. Has some variables that are initialized for the start time and the stop time and whether the timer is running. Has the various setups for both the LED and the button and the sensor. Here's the main loop, and it'll check whether or not the timer is running and the button's pressed. Once the button's pressed, it'll read those accelerometer values and also will apply corrections, and note these corrections here, which I'll go over later, how to get those. It takes those accelerometer values and calculates the tilt values for the X, Y, and Z directions. Then it determines if the tilt in the Z direction is greater than a certain threshold. In this case, I've used 18 degrees, and I'll show later how I got that value. If the timer's running, it'll check whether the board has been tilted for at least 400 milliseconds, and if it has, then it'll stop the clock and calculate the end time and display that. And while the board is not tilted past that threshold, the timer will keep running and it will continually display the time. And this is the code that I use to determine that 18-degree tilt threshold. Again, it has the same include statements and initialization, reads the accelerometer values, and then calculates those tilt angles. And here we have a display so that it will display on the LED the tilt in the Z direction. And I run tests tilting the board to see at what angle it touches the ground. In this case, it was 18 degrees. And just as a note, for determining these accelerometer offset values, what I do is I use the same code and here have it first display the accelerometer X value, and then I rerun it using the accelerometer Y value, and I use a level to determine what the accelerometer values are when the board is completely level, and then say that the accelerometer X value in that case was negative 700. I add 700 here to correct for that offset. Similarly for the accelerometer Y value. And those corrections are applied because when this sensor is attached to the board, it's not completely level, so you have to subtract out or add the correction values to get the right accelerometer values for the tilt calculations. Then, once it's been all hooked up, you place the breadboard into the opening in the plastic member that was created. Turn it upside down, being careful to make sure that all of the wires are contained within the inner portion of the plastic member, and turn it upside down and screw it back together. I would also mention that I use some tape to hold the breadboard in place so that when I turn it upside down, it stays within the plastic member. Then, once it's been screwed back together, the board is ready to operate.